Now we start looking at some examples of some functions in terms of their limit. One of the classic examples for looking at limits is what we call the greatest integer function. Now the greatest integer function has a special notation, g of x equals bracketed x. Now that means, okay, that the function will assume all values of x in its domain, but only return to you integer values in its range. As an example, if you plug in an x value of 1.265, it only returns to you 1. If you plug in the x value of 0.123, it only returns to you the integer component of 0. If you put in the x value of 4.623, it only returns to you the integer value of 4. So in other words, it truncates all the decimal values, only returning the integer component of whatever value is given it, okay? And it's a rounding. For if you were working with money, everything would be terminated to the integer, where the integer might be cent, okay? Dollars and cents perhaps, okay? So the appearance is this stepwise progression. Here's the stepwise progression of a greatest integer function, okay? Now, so this is a classic example for explaining the left and right hand limit and why the limits do not exist, okay, for any integer value. So we say to us, okay, here, let's ask what happens as we approach 0, okay, as x approaches 0. Now again, in order to determine what happens as x approaches 0, we have to look at it coming from the left side and coming from the right side. So we say, okay, let's examine the limit as x approaches 0 from the left side, value slightly less than 0, okay? And when we look at that, we're riding along right here, okay? And, okay, we're coming at a value of -1. All right, we're coming towards a value of -1. But if we're evaluating coming from the right side of 0, you can see we're approaching the value of 0. So since we're not approaching the same value from the left as we are from the right, we're going to conclude the limit does not exist at x equals 0. So we move to examining what happens as we approach 1. So as we approach 1 from the left side, okay, the y value is and always will be 0. As we approach, okay, 1 from the right side, the y value is and always will be 1. So since we are not in agreement from both the left side and the right side, the limit at 1 does not exist. And we could go on and on for that, and we would see, okay, one last time, limit as we approach 4, okay, is going to be on the right side, it's going to be 3. We have another step up here. From the left side, it would be, from the left side, it would be 3. From the right side, it would be 4. So therefore, we're going to say, okay, just from this appearance, at every integer value, the limit does not exist because approaching it from the left, approaching it from the right do not agree. Since the left and the right hand limits at any integer are not equal, we conclude the limit does not exist at any integer value, okay? All right, onward, okay? Here's another function. The simple hyperbola y equals, or f of x equals 1 over x. Well, obviously we know x can never take on 0. So that's probably the point where we're going to ask to find the limit at x equaling 0, okay? Now, we can't evaluate the function at x equals 0. So we have no choice but to ask, what happens on the left side and what happens on the right side. So we know our graph, we know there's an asymptote along the y-axis, that's the x value of 0, and we say, well, what happens as we approach from the left side of 0? That would be for the negative values. Well, obviously, we're riding along the curve, and we're going to be approaching negative infinity, okay? As we're approaching 0 from the right side, okay, then we can see we're in the positive sector up here, and we're going to rise towards positive infinity. So one side moves towards negative infinity, one side moves towards positive infinity, okay? They're totally divergent directions. The limit as x approaches 0 does not exist, okay? Here's another one, our Atari function, if you will, okay? The function f of x equaling 1 over x minus 2, x minus 1, the quantity squared, okay? Of course, with the squaring in the denominator, we're guaranteed that we're always going to be positive. The y values are always going to be positive in this function. And owing to the asymptotic behavior at 1, okay, we're moving towards that in on both the left side and the right side towards positive infinity. So, okay, the question is going to be what happens, okay, the obvious question in terms of limits is going to be asking for the limit at this curious value of 1, because at the value of 1 the function is undefined, yet that does not imply that the limit does not exist until we take a closer inspection of it, okay? And looking at it from a closer inspection, we can find, we should agree, simply from the graphical approach, as we approach 1 from the left side, we move towards positive infinity. As we approach 1 from the right side, we also move to positive infinity. Therefore, we could say that the limit as x approaches 1 is equal to infinity. Now, this might seem to be a disagreement with our earlier statement about the limits, which said we had to approach a definitive value, okay? Now, since we are approaching infinity, both from both the left and the right, saying that the limit is going to be equal to infinity is perfectly valid because it tells you something, okay? Some would argue that that's not a definitive value and therefore the limit does not exist, but saying that it is equal to infinity is more informative than saying it does not exist, okay? Because in this way we imply that from both the left and the right we're moving along an asymptote approaching infinity. So therefore we're going to agree that it is infinity. Okay, we'll come back and look at some more examples in the next video.